So, welcome to the lecture on computing the likelihood score on phylogenetic trees. Let's first think about what is given when we ask this question: how do we compute the likelihood on a tree? So, to make things a little bit easier, what we assume to be given is a multiple sequence alignment, a fixed tree topology with given branch lengths, a model of nucleotide substitution, and we simply assume that we can calculate the transition probability matrix, so the probability of a state of a nucleotide X changing into a nucleotide Z within time B, which is just like a branch length or the time. So we assume that this transition probability matrix that is essentially defined by our model is given, and that we can compute the transition probabilities for any value, any positive value of B. Okay, so let's first think again about what the likelihood is. So here, the probability is the probability that the tree generated the data, right? So this is a generating process, and this is actually the likelihood of a tree. So what is the probability, or what's the likelihood of observing the tree given the data? So what is the likelihood that this specific tree generated this data? So we just read that as well, the likelihood of the tree. What is the likelihood of a tree given the data? And that's what we actually want to compute. And just to recapitulate the differences between likelihood and probabilities. So likelihood is, well, if I do 10 coin flips and I obtain 10 heads, my question is like, what's the likelihood that the coin is fair? And the probability is just the probability of landing heads up 10 times. Okay. So what's the likelihood of a given, of observing a tree given the data? And this is just the product of this per site probabilities for every side in the alignment, to observe the nucleotides for every side of the alignment given the tree, right? And we'll see what this induces. So SI is just one side of the alignment, I, and key question is, so we have this product here over probabilities. What might be problematic about this term? And the answer simply is that, well, what is problematic about this term here is that we're multiplying potentially a very large number of probabilities with each other. So assume an alignment of 100 million sites or something like that. Then the values returned in this product will become smaller and smaller and smaller, and converge towards, get closer, not converge, but get closer and closer and closer to zero. And this is a numerical issue because we cannot represent such very, very small numbers on a computer. So we risk experiencing numerical underflow. So what we typically do is that instead of computing the product of over the probabilities, we compute the sum over the logarithms of those probabilities. So that's the actual reason why we're not using the likelihood directly, or reporting the likelihood directly when we're doing phylogenetic inference, but we always report the log likelihood. So we take the logarithm on both sides, and then this product gets transformed into a sum over the logarithms of the probabilities of all alignment sites. Right. And so what is shown as T here is actually the model, right? So it doesn't only consist of the tree topology, but it also comprises the branch lengths as well as a model of nucleotide substitution. And so what is generally done when describing those models, you can see that in a lot of papers, is that all those parameters that make up our model are typically lumped into this parameter vector theta that we're also going to see, or have already seen, in the lecture about MCMC methods. Right. And so for the rest of this lecture, we will actually just focus on the probability of observing a site, so the nucleotides at the tip, given a certain tree topology, right? Because if we can do that for one side, we can do that for all sides and thereby compute the overall likelihood of the tree. Okay, so first assumption, I've already mentioned that as for parsimony, for likelihood as well, we assume that the sides evolve independently. So we're given our multiple sequence alignment with the sequence names, the tax names written over here, and then this is our sequence alignment length n, and we're just interested in computing the likelihood of observing a single side given the alignment in the tree. Okay, then we're given like a fixed tree topology with fixed branch lengths. So we're not doing any tree searches here, or we're not altering the branch lengths. And finally, we're given our model of nucleotide substitution M that is then encoded or is used to actually calculate the transition probability matrix P for going from a nucleotide state I to a nucleotide state J within time t. Right. So, as I said before, the overall likelihood is then just like the product over the per side over the per side likelihoods, and to make this numerically tractable, we typically take the sum over the logarithms of the per side likelihoods. All right, and so our transition probability matrix, as I said before, is given a branch length or time t, and our states are just from the set AC GT. Okay, and this transition probability matrix actually tells us what is the probability of being in state J after time t if we started in state I. And of course, and that's why we did all the lectures about, or did this lecture about the Markov models, we assume that this transition probability matrix, Pij of t, is actually a Markov process. Another thing we need, since we're talking about Markov processes, is that we need the equilibrium frequency vector P that comprises the equilibrium or stationary frequencies of A, C, G, or T. Okay. And finally, another thing that we need to assume for efficiently calculating the likelihood of a tree is time reversibility, right? So basically, we assume that evolution occurred in the same way if followed forward or backward in time. And this boils down to the following equation that must hold. So the prior probability, or the equilibrium frequency of I, multiplied with the transition probability of going from I to J within time t, must equal the stationary frequency of state J multiplied, and here there's an error in the slide, with the transition probability for going from J to I in time t, in the same time t. So the two indices here should actually be flipped. Okay, so here's the question, given those preliminaries, what is the likelihood of this tree? First thing that we do, because we're assuming time reversibility, is that we can just like place a virtual root anywhere in this tree. So in any branch and at any position along that branch, so we could also have chosen this one here, we may just throw a virtual root at the tree and then drag it up like that, and now our tree looks like this, right? So we have the nucleotides from our alignment side located at the tips. We have a couple of branch lengths and a couple of inner states, I1, I2, I3. And so we've just designated this node here, I1, as the virtual root. Okay. So how do we go about computing the likelihood of such a tree? So for the sake of simplicity, let's initially forget about the fact that we don't know what the inner states are here, but let's assume that the inner states are given. And so now, what is the likelihood of the tree if we interpret this tree as a Markov diagram, right? And so what would be the likelihood of the tree here? It's very simple. So the likelihood of this tree for or this specific alignment site is just the prior probability of being in state A at the root, so in the starting state, so keep in mind that we're considering this as a generating process. So what is the likelihood that this tree generated the observed sequences here? So this is the prior probability of being in state A at the root, so this should be PA, and then we multiply that with all events that can happen. So for observing those nucleotides at the tips, we first of all need to be in state A at the root, and then go from A to A again within time B1, and then go from this A to A again within time B2. Then we need to go from this state here, A to A again within time B3. And so we're done with this left subtree, then we go to the right subtree. So what must also have happened at the same time, so here's the AND again, that means that we need to multiply probabilities. So what must also have happened is that we went from A to T within time B4, and then from T to T within time B5, and then from T to G within time B6. So here you can see that all those events must have happened in order to observe this pattern A, T, and G here at the tips for the given tree with given branch lengths and given inner states. So once again, we're multiplying probabilities here, because to observe the data at the tips, given the tree, the initial state must be A, right? So this is a prior probability of observing A. And then this happened, this transition from A to A, and this happened, and this happened, and this transition from A to T within time B4 happened, and this happened, and then finally a transition from T to G within time B6 happened. So if you think about this like in a logical natural language argument, it is kind of clear that we need to multiply probabilities here. So just keep in mind this AND. However, unfortunately, we of course don't know the inner states. So the question now is, well, what are the possible evolutionary histories that could have given rise or could have generated the data that we observe at the tip? So what could have happened here, here, and here, such that we observe the data at the tips? And so now, well, which possible evolutionary histories or which possible ancestral states or transitions from A to something else here could have given rise to what we observe at the tips? So it could either be this, right? What we've seen previously, all inner states are an A, or it could be this, right? So it could be A, and then C here. So then we just need to calculate the transition probabilities from C to G and C to T to get the likelihood of this tree, given that the inner state here is C. Or it could be this, right? It could be, we could have a G here, or this. So this should be a T here. So this slide is duplicated. So here's our T, right? So it could be A, and T in terms of inner states. Or maybe it could be this. We have an A here at an inner state, an A here at the other inner state, and here we have a C. Or it could be this, right? So we go from A to G here, but here we still have an A, etc., until we've kind of enumerated all possible assignments of nucleotides to the inner nodes of the tree, such that in the end we also compute the likelihood of an evolutionary history where all inner states were T. So you can see it by those red ors here that we must be summing over something. And so the likelihood of the tree for which we don't know the inner states is the sum over the likelihoods of all possible assignments of A, C, G, and T, so all possible evolutionary histories, to the three inner nodes of the tree, right? So I just need to enumerate, in a naive way, I just need to enumerate all possible assignments of nucleotides to those three inner nodes, compute the likelihood for each of those assignments, and then just build the sum or compute the sum over those likelihoods for all distinct assignments, and I get the overall likelihood for that tree. So here the bad news is, or what might initially irritate you, is that if I think about the possible number of assignments of those four states A, C, G, T to the inner nodes, as I have three inner nodes and each inner node can be assigned four distinct nucleotides, I have 4 times 4 times 4, 6, so meaning 64 possible assignments in our example. And this is a very small tree. But if you think about like really large trees and having to enumerate all possible assignments, this really sounds very compute intensive because I have this exponential growth in the number of possible assignments depending on the number of inner nodes. So the question is, can we do better? And fortunately we can, otherwise we would not be able to conduct phylogenetic inference under likelihood models. And this takes us to the Felsenstein pruning algorithm. So once again, as before for parsimony, what we do is this kind of post-order traversal of the tree, right? So we walk along the tree, and every last time we visit one node, we actually do some computations at this node. So this is indicated by the CPU sign here. So we do some computations here. We continue walking along the tree. The last time we visit inner node I3, we do some computations here. And then once we finally return to the root after our walk over the tree, we also do some calculations at the root. Okay, and so as I've said before, as for parsimony, we just store some sort of vectors at the inner node, so here they're called conditional likelihood vectors, that tell us something about the subtree that is located below those vectors, below this node. So this is why they're called conditional likelihood vectors, because they give us the probability of observing A, C, G, and T conditional on or given the subtree that resides below the vectors. And so this kind of like this intermediate storage of results of what's the probability of observing A, C, G, or T here for the given subtree allows us to compute the likelihood in a substantially more efficient way. Right. So here's what happens. So assume that we were able to compute the conditional likelihood vectors for this inner node and this inner node. So how do we compute the conditional likelihood vector entries for the root node, so for the entire tree? So here, well, what's the probability of observing an A here? It is the probability of doing a transition along this branch here, B1, and ending up in an A again. So it's a probability of going from A to A in time B1 multiplied with the probability that we have an A here. Right? So this is one way, one possibility that we could end up with an A here. So we are in an A here, we do a transition from A to A along this branch, and we end up in A again. Or the other thing that could have happened is that, here we assume that we're in a state C, and we're doing a transition from C to A within time B1, so along this branch here. This is also one possibility how we could end up in an A here. Or we could, of course, go from A to G along this branch B1 here, and then we still must multiply it with the probability of actually being in G at this inner node here. Or we may assume that here we are in state T with a certain probability, and then we're going from T to A along branch B1 such that we end up in A here. So you can see the or again, which tells us something that probably we just must multiply over those four possibilities of how we could have gotten from an A, C, G, or T here to an A at the conditional likelihood vector at the root. And so to end up in A, one of those events must have taken place, and there must also be an A coming from the other side, from the other subtree. So here we do the same exercise again. So, well, how could I end up with an A using the conditional likelihood vector from the right side? Well, it could be, if I was in a state A here, I need to transition from A to A along branch 4, or if I was in state C here, I need to transition from C to A along this branch here, etc., etc. So, and this basically is the Felsenstein pruning algorithm, right? So you consider all possibilities of going from the child vector to one specific discrete entry in the root vector, and then just, so you compute the sums, which are shown here, right? So this is the transition probability from A to any other state along this branch BI here, multiplied with the probability of being in that state at the child vector, and then this sum for the left subtree is then multiplied with the corresponding sum of products of the right subtree, because in order to be in A here, we must have gotten from some state along BI to A here, but also from some state along BJ to A from the other side. So this should hopefully, this kind of and argument should hopefully help you to understand how we come up with those equations. So the best way of memorizing that is just to remember me shouting and or in this lecture. Okay. Right. So this is again what happens, right? So the signal coming from the left and from the right child must both go to A, so this is an AND here. But then there are various ways of ending up in A coming from the left branch or the left child, and there are also different ways of ending up in A coming from the right branch. And of course, then you do exactly the same exercise for all three other remaining states in this conditional likelihood vector here at the root. So then essentially what you do is that you just do that recursively via post-order traversal along the tree, and you're done. Okay, so here's like a full picture of that. I've shown that in the parsimony lecture before. So we do this kind of bottom up from the leaves toward the virtual root. And just to remind you of that, so this is how we actually initialize the conditional likelihood vectors at the tips of the tree where we have data. So the probability of observing an A is 1.0 here, and the other probabilities for C, G, and T are 0.0, just because we have like an actual observation here. And so if you have a T, you set the last entry to 1.0. If you have a G, you set like the third entry to 1.0. And that's it. Okay, and then finally, well, how do we calculate the likelihood at the root? So this is something I didn't mention. And the likelihood at the root is, well, so we have the conditional probabilities of observing A, C, G, and T here. So that's what we already calculated. And now the missing part is that we need to multiply those probabilities with a prior probability or stationary frequency of observing an A. So the likelihood at side I is just the prior probability of A multiplied with the conditional probability of A plus the prior probability of C multiplied with the conditional probability of C, etc., etc. Okay. Now, this is just another way of showing the likelihood calculation at the root here. So basically, those two terms here, or this product of those two sums, corresponds to our conditional likelihood vector at the root. So oftentimes this is not explicitly stored, but just directly computed to say storing the vector here, and then the root position, and this is the sum over the different starting conditions here with the stationary frequencies, and then B1 and B4 just give us the placement of the root along this branch here. So the reason why time reversibility is important, I've explained that before, is that we can arbitrarily move the position of our root along this branch here without changing the likelihood score, right? So as long as your model is time reversible, it doesn't matter at all where you place your virtual root here, because evolution occurred in the same way, it followed forward or backward in time. And so it doesn't really matter where you place the root. So either if you bisect this branch at B1 and B4, or you bisect it at B1 prime, B4 prime, you will actually obtain exactly the same likelihood. And so this is the reason why this is true is that it's a property of the transition probability matrix as long as it's time reversible. So another thing that we can do to simplify calculations and economize a little bit in calculations is that typically you would set B1 prime to 0, so just put the root directly here next to this inner node, and B4 prime just to the sum of B1 and B4. So that's how it's often done in practice. And of course, this observation does not only hold for this specific branch we selected as the root branch here, but it can be applied, the argument can be applied recursively to the tree, so it doesn't matter neither where along a branch we place the virtual root, nor into which branch we place that virtual root. It doesn't change the likelihood of the tree, once again, as long as our model is time reversible. Okay, so big question that we need to answer is, well, we've assumed that we're given this transition probability matrix for transition from state I to state J in time t, but where does it actually come from? So we've seen it before when we talked about general Markov models and continuous time Markov models, but let's have a closer look. So first we consider an instantaneous rate matrix of transition rates in time dt, and we can see here that all states are connected with each other by some rates, like which are typically denoted by lambda. So here is the rate of going from A, the instantaneous rate of going from A to C, A to G, etc. So what about the probabilities of staying in the current state? We don't actually need to care about them because they are given by the properties of continuous Markov chains. So remember that those rows in this rate matrix for time dt actually need to sum to 0, because for the real matrix, for the transition probability matrix P, the rows need to sum to 1. Here those rates need to sum to 0. Right, so if you don't remember that, just have a look at the lecture on Markov chains again. And so basically the rates of staying in the same state A are just given by adding up the remaining rates of going to other states, so from A to C, A to G, A to T, and then putting a minus sign in front of that. This will guarantee that the rows of our rate matrix actually sum to 0. Okay, and so another way, we've also seen that before, another way of representing this Markov diagram here for instantaneous time dt is to represent it in an instantaneous rate matrix, right? So basically here, typically the diagonal is denoted by stars because it is given by the non-diagonal elements, and because of, well, or to make this time reversible, the matrix also needs to be symmetric. Okay. Right, so as I said before, the diagonal values are given by the off-diagonal values. This is the property of the R matrix, so such that the rows sum to 0. All right, another thing, of course, that we need to fully define our model, and a thing that is also connected with the transition, the rate matrix, is that we need an equilibrium frequency vector P for A, C, G, and T, for the 4 states in our Markov model. And of course, the frequencies need to sum to 1. So let's look at some very simple models. So the most simple model you could ever imagine is a Jukes-Cantor model. So here you would assume that all rates are equal, right? So all transitions happen at the same rate. And you would also assume that all stationary frequencies are actually identical, so 1/4, 1/4. Then if we want to make this a little bit more complicated, we can assume that, well, still we only have one rate of evolution here, but the stationary frequencies are allowed to be different. So this is the Felsenstein 81 model, and then we can start adding more and more parameters to our model. So this is the Kimura 2 parameter model from 1980 that basically distinguishes between transitions and transversions. So here we're considering a rate matrix with 2 distinct rates, lambda and zeta, that yields a slightly more complex model, but on the other hand, we still assume that our stationary frequency vector, all frequencies are identical to 1/4. Then we have the HKY 85 model, so you see how this works. So we're continuously relaxing the restrictions in our model. So here we also have 2 parameters, lambda and zeta, but now we also allow the stationary frequencies to be different. And then finally, the most general model that we can come up with for 4 states, or the most general time reversible model that we can come up with for 4 states, is a general time reversible model of nucleotide substitution that was introduced in 1986. And so this basically here, every rate is different. So we have a total of 6 rates: alpha, beta, gamma, delta, epsilon, and zeta. And the stationary frequencies also do not need to be identical. And of course, you can come up with many more models, intermediate models between GTR and HKY 85. So you could say that, well, let's forget about the Vita here, maybe from A to G. I also go with a rate of alpha. So there are various ways of defining those models, and in total, given all possible configurations of parameters here in this rate matrix, there are like 203 possible configurations. So from the most complex one, GTR, that has 6 rates, to the most simple one, which is Jukes-Cantor, that has just 1 rate. There are many ways of setting up intermediate models with 2, 3, 4, or 5 rates. Another very important thing to notice is that the rates in our rate matrix are actually relative rates. So their absolute values do not matter. So the only thing that matters is the values between the rates relative to each other, which is the reason why they're called relative rates. So this means, in order to simplify things, that we can just, because we're dealing with relative rates, that we're just setting zeta, the last rate here, to 1.0. So we don't need to estimate a rate for zeta, but just need to estimate the other 5 rates relative with respect to a rate of zeta that equals 1.0. And that's actually how it is done in practice. So although this GTR model has 6 rates, this means that it only has 5 free parameters that I actually need to optimize. because the rates are relative. Okay, so here is just again an overview over the model hierarchy. So the most simple model is Dukes-Cantor. Then we added unequal frequencies or more parameters like a second parameter. And then here we added unequal frequencies, or coming from the other side, more parameters. So this made the HKY85 model. And then finally we ended up by relaxing the assumptions on the rates. We ended up with the GTR model, and of course in between there are other also named models as well as unnamed models, depending on the number of distinct rates they contain. Okay, so this is actually a rate matrix, but time reversibility would require us in general that the prior probability of I multiplied with the rate from I to j equals the prior probability of j multiplied with the rate from j to I. So, of course, if all our stationary frequencies are identical, so meaning that they have a probability of 25% or a frequency of 0.25, this automatically holds. But as soon as I allow the stationary frequencies to be different from each other, this time reversibility property does not hold anymore for our rate matrix. So we need to do something about that, and the solution is to introduce a so-called Q matrix. And this Q matrix, so this is a little mathematical trick, this Q matrix is defined as the product of the diagonal matrix of this stationary frequency vector. So this is what the diagonal matrix of this looks like. Here we have zeros and here we have zeros, so there's just data on the diagonal here, multiplied with the rate matrix. And this matrix then, so you can just like do the calculations on your own, doing a little bit of matrix algebra. If I do this, then the property, well, then Q, actually not R, but Q is actually time reversible. So we just multiply with the scalar here. Keep in mind that those rates are relative. So as long as we maintain the proportion of those rates to each other, so this remains constant, we can multiply that with any scalar. Okay. So that's how we set up our rate matrix and how we end up having this rate matrix R, but also this Q matrix Q. But how do we actually compute the transition probability matrix for a given time t from this rate matrix Q? So, as we've seen in the lecture on Markov chains, the transition probability matrix T is given by the exponentiating the matrix exponential e to the power of q, that's our Q matrix, multiplied with t. And of course this can be approximated by applying the series expansion of the exponential, right? So this would be one way of doing that. But we are also interested in other ways of doing that, so we want to compute this transition probability matrix exactly, although this could be a solution that works in many cases. So I will generally spare you the details because this is numerically complicated, but in general, for instance, for GTR, what we actually need to do is to apply an eigenvector eigenvalue decomposition of Q to calculate the transition probability matrix for T. So the way this looks like is that we have the matrix as well as the inverse matrix of the eigenvectors of Q on the left and the right hand side of this equation, and then in the middle we're computing the exponent of the diagonal value Li of the vector of eigenvalues of Q multiplied with the time. And so note that this is a scalar expression, right? So the diagonal value Li, so this is just the ith eigenvector of Q. So this is basically just the scalar calculation or a scalar invocation of the exponential function, and then the result is just put into a matrix, and thereby we can compute the transition probability matrix. So I will spare you the numerical details and how we actually do that in practice. Okay, so far we've only really seen how to calculate a likelihood on a given fixed tree topology with given fixed branch lengths and given fixed remaining model parameters, right? So we assume that the rates in our rate matrix were just given to us. So this is just how we compute the likelihood on one set or on one instance of all the parameters that we need to optimize. So computing the maximum likelihood score is much more complicated, as it requires, on the one hand, functions for optimizing continuous parameters like the branch lengths and the rate in our rate matrix, so optimize with respect to the likelihood score. And of course, we also need functions for optimizing the tree topology, so for traversing this discrete space of trees. So we need functions to optimize continuous parameters, but also functions for, well, attempting to optimize this discrete parameter, which is the tree topology. So this is the end of this lecture here. I'll spare you the details on numerical optimization methods for likelihood calculations, but I hope that you got an idea of how we compute the likelihood in principle.